This is an example now of a conundrum that we ran into in class. So let me show you what's going on here. This example over on this side, we're just going to call this a normal ramp. This is an object sliding down a ramp. Now it could be that this is an object sliding up a ramp, etc. And of course if there was friction that would go one way or the other. So notice the acceleration is down the ramp. So if again, if you don't already know that this angle and this angle are the same, you can see that as this were to go down, imagine this is a board that's fixed to the ramp, and this is something hanging down, a string with a mass on, like a plumb bob or something. And as this thing falls down, this angle will decrease. I have another video like this on YouTube. Check that out. So if this is mg, the weight of the object, and I use mg because I think that there's no confusion there. And if this one is adjacent, then this is mg cosine theta. And this one is mg sine theta. So in the final analysis of this, we can see that if we change the axes like this, we make this the positive x-axis, make this the positive y-axis. Now you might ask, why am I doing that? I used to tell my kids it was because if there's friction on here, then you have two forces that are parallel or perpendicular, or sorry, parallel to the axes and one that is not, so you're only resolving one. Now that I've done a lot more physics, it's because of this. If the acceleration is tilted like this, you want to tilt your axes. That's just basically it. There are almost no examples where you wouldn't want to do that. If you have an acceleration in a particular direction, one of your axes should be along that acceleration. So in the y direction, we have mg cosine theta equals Fn. Now you might say equals ma, but again, unless this is much, much greater, you're pulling up on this object, it's not going to be accelerating in this direction, only this direction. So those two forces are equal. Well, then in the x-axis, and I'm going to put that over here for a particular reason that you will find out later, in the x-axis, we just have mg sine theta equals m times a, so this acceleration equals g sine theta. And if you remember your trigonometry, the sine of 0 degrees is 0, so let's write this at 0 degrees, then a equals 0, because the sine of 0 degrees is 0. And at 90 degrees, sine 90 degrees equals 1. So a equals g, and it's just in free fall. No big deal there. All right. Well, now what is this over here? This two situations that I can find this way. This would be front view of a car on going forward around a tilted ramp or a tilted corner. That works, right? So you're going around a corner, and this is the car going around that tilted corner. Okay, that's one example of what this could be. Okay, the other that this could be an object on a ramp, and the ramp is accelerating to the right. Okay, you can actually do this with a momentum track. Just put a cart on it, push the track very quickly to the right, and you will see the cart go up, or you could even keep it stationary. Okay. Now, as we said before, you see how the acceleration is now this direction. If that's true, then I'm absolutely going to make my xy axis this direction. That's now going to be my x-axis. That's going to be my positive y direction, and I'm not going to tilt my axes. Again, you should see that this and this are the same angles. Look over here, it would be the same angle. There's theta, 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 once again theta, and you might say, well, why didn't you draw this one? Well, we'll talk about that in a bit. Anyway, so this angle and this angle are the same. Let me remove that one. It will get in our way. So now I break things up into their x and y directions. In the x direction, we get that this part right here is actually a part of the normal force now, because notice it is absolutely perpendicular to mg. So no portion of mg is in this direction, because horizontal is not vertical. So in the x direction, we have, again, if this right here is adjacent, this is Fn cosine theta, and this one must be Fn sine theta. So in the x direction, we have Fn sine theta equals ma. Now, if this right here is a car going around a ramp, so that, again, imagine a big oval ramp and you are looking at a part as it's coming towards you, then this would be a centripetal acceleration, and that right there would be v squared over r. If it's just the ramp being pushed this direction by a force, like a wedge or something, well, then it's just a. And you could use normal kinematics with that. Well, what about in the y direction? And again, there's a reason why I'm putting this here. So in the y direction, notice that Fn cosine theta equals mg. And now we've run into our conundrum. Notice here that mg cosine theta equals Fn, and here Fn cosine theta equals mg. These are not the same. They're both objects on ramps, but these are not the same expression. You'll notice here that mg is bigger than Fn, because if I solve for mg, I get mg equals Fn over cosine theta. And it's the same cosine theta, isn't it? Here, Fn or mg equals Fn cosine theta, so Fn is bigger. Now, I am going to explain to you why this conundrum. But what I would suggest you do right now, if this is a teacher, I would suggest that you put this on pause and you let your kids kind of fight this out. It took my kids a good 30 minutes to come up with this, maybe 15, 20, and let them actually fight through this. If you're doing this on your own, I suggest you stop and you think about this. So I'm going to do a pause here for just a few seconds, and then I'm going to start over again. All right. Now, here's what's going on. If you hadn't already sniffed this out, if your physics instincts weren't that good, it all comes down to this. This is the important part. There's A and there's A. They are not in the same direction. So, on this side, mg is bigger than Fn, because mg is providing the acceleration. So let's write that down. So mg, the weight, must provide the acceleration and oppose Fn. So mg is bigger. And over on this side, try to find my cursor, there it is. In this case, Fn must provide the acceleration and oppose mg, or gravity. So Fn is bigger. Now, even though this conundrum seems like it's a big issue, as long as you were to do these steps, and let's make these very, very clear, and this works on all of Newton's, anytime you use Newton's second law, this will work. First, draw a force diagram, or on your actual diagram that you have, put in all of your actual forces. These are external forces, not internal forces. Then you can figure out where if you know your acceleration, that would be number 2, pick a coordinate system so that your acceleration is parallel to your coordinate system must be parallel to the acceleration. Again, x is parallel to a here, x is parallel to a here. Once you have that, then you can break up your sine and cosine. Use sine and cosine to break up your forces into the x and y direction to find their components, and then it's a simple matter of finding, setting them into your x and y directions. Okay, and then even something that seems like a conundrum here ends up working out pretty well. Now, I just want to show you one last thing before I go here. Notice in this case, mg here would be the largest side of this right triangle. But over here, it turns out that Fn, let's see if I can draw that a little bit nicer. Turns out that Fn is the big side of this triangle, and then the rest of that triangle would be here, And notice that Fn here is the biggest side. So the triangle is not actually the same. All right.